Today we're going to be solving trig equations. So before I get into some examples, I want to talk about the difference between an equation versus an identity. First, a trig identity. An identity is true for all values. For example, sine squared theta plus cosine squared theta is equal to 1 no matter what angle we plug in there. A trig equation, on the other hand, is true for specific values. For example, if I had sine of x equals 1, there are specific values that I can plug in that'll get a 1 for sine. Okay, so our first example, we're going to solve 2 sine x plus 1. So this is obviously not true for all values. We're trying to find the specific values that it is true. It'll start like any normal algebra problem. So I'll start by subtracting 1 and then divide by 2. Okay, so we're looking for where sine of x is equal to negative 1/2. Now the answer to this is there are an infinite number of solutions. So think about the graph of sine. If I had the graph of sine, there's an infinite number of times where sine is going to equal negative 1/2. So how we're going to have to, there's different ways we can answer this question. So let's say I want the solutions between 0 and 360. So for this, we're going to look at the unit circle and find where the y values are equal to negative 1/2. So we go to the unit circle and we find the two locations where it equals negative 1/2, which is going to be here and here. And if we're asking from 0 to 360, we want the degrees. So that's going to be 210 and 330. Okay, if I asked from 0 to 2 pi, it's still those same two locations, but we want the radians, so 7 pi over 6 and 11 pi over 6. Okay, there's other ways we can ask this question. I could ask for what's called principal values. Okay, principal values is going to be the inverse function. So that's going to be the highlighted unit circles from last semester. So for sine, that means we're looking for an angle between negative pi over 2 and pi over 2. So it's going to be that same location that we were looking at 11 pi over 6, but rather than calling it 11 pi over 6, it's going to be negative pi over 6, because that's the one location between negative pi over 2 and pi over 2 where sine is equal to negative 1/2. Okay, lastly, let's say I want all of them. Okay, well, to do that, we're going to take the two unit circle values and add either 2 pi k if we're talking about radians or 360 k if we're talking about degrees. So I'm going to go ahead and just do with radians. So that's going to be 7 pi over 6 plus 2 pi k, 11 pi over 6 plus 2 pi k, where k is an integer. Okay, thinking about the unit circle, this just means we're going around another rotation. K being an integer means it can be positive or negative, so we can subtract 2 pi, we can subtract 4 pi, and so on. So for most questions, you're not going to be asked for all of these. You'll be asked for a specific range. And if they don't say, you're going to assume all values. Okay, so the first couple of examples, we're going to solve for all values. Okay, so our first example, 5 cosine x equals 3 cosine x plus root 3. We're going to solve it just like you would any normal equation. So first I'm going to subtract this 3x, or 3 cosine x. So I'm going to have 2 cosine x is equal to root 3. Then we'll divide by 2. Then we go to our unit circle. So we're going to find the two locations between 0 and 360 where our cosine is root 3 over 2, where our x is root 3 over 2. So that's going to be here at pi over 6 and at 11 pi over 6. And then we're going to add 2 pi k. Now we should usually define k every time, but I'm okay with just the understanding that we all know it's going to be an integer. Okay, so we have 3 tangent squared x minus 4 equals a negative 3. So we'll start by adding that 4 over. So negative 3 plus 4 is going to be 1. I'm going to divide by 3. Is 1/3. Then I'm going to take the square root. But when we do that, we have to acknowledge that if tangent squared equals 1/3, that value could be positive, but it could also be negative. So this is 1 over root 3, which we are more used to seeing it as root 3 over 3. So we're looking for, in this case, the 4 locations where tangent is negative root 3 over 3. It's not a bad idea to add those tangent values to your unit circle, but they're going to occur when the y value is 1/2 and the x value is root 3. So that's going to be at pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And then we'll add 2 pi k to all of those. Now in this case, you could make it a little bit cleaner because numbers like 5 pi over 6 and 11 pi over 6 are pi apart. So you could say pi over 6 plus pi k and 5 pi over 6 plus pi k, and you wouldn't have to include these, but this is just as acceptable. So these 4 answers plus 2 pi k. Our next set of examples, we're going to solve on the interval 0 to 2 pi. Remember, this notation means the 0 is included, but the 2 pi is not. All right, so we have this equation, so they're getting more complicated. One thing to be careful of, it might be tempted to just say, well, just divide both sides of this equation by cosine. But if you do that, you're going to eliminate solutions to this problem. So you don't want to ever divide out a trig function. What we're going to do here is subtract. So I'm going to have 2 sine x cosine x, and I'm going to subtract root 3 cosine of x. Okay, then what I can do is factor out that cosine. That's going to leave me with 2 sine x minus root 3. Now using the 0 product rule, and it only works if this is 0, that means if this is 0, one of these two things is 0, or anything that makes this 0 or this 0 are solutions to this equation. So either cosine of x equals 0, or 2 sine x minus root 3 equals 0. So we'll deal with each of these individually. So we're looking for everything between 0 and 2 pi where the x value is 0, and that's going to occur at the top of the circle at pi over 2, and at the bottom of the circle, 3 pi over 2. This one, we're looking for sine of x, we're going to add root 3 and then divide by 2. So we're looking for where sine of x equals root 3 over 2. So we're looking for the y values to equal root 3 over 2. So that's going to be at pi over 3 and 2 pi over 3. Definitely going to want a unit circle handy when you're solving these equations. So our next example, 2 sine squared x plus sine x minus 1 equals 0. So this should trigger a algebra 2 response of I have a trinomial here, and what we're going to do is factor. The good news is they're going to be pretty simple factoring. So the two things that are going to multiply to get a 2 sine squared is going to be a 2 sine of x and a sine of x. To get a negative 1 here, we've got a positive 1 and a negative 1. We just have to figure out which one goes where in order to get this middle term. Well, I'm going to multiply the 2 times a positive 1 and this sign by a negative 1. If I FOILed it, we'd get 2 sine squared plus 2 sine minus 1 sine, which makes this plus, and then a negative 1. Okay, again, we're using our zero product rule, so either 2 sine x minus 1 equals 0, or sine of x plus 1 equals 0. So sine of x equals 1/2, or sine of x equals negative 1. Again, we're going to refer to our unit circle. Our y values are 1/2 at pi over 6 and 5 pi over 6. Our y values are negative 1. At the bottom of the circle, 3 pi over 2. So factoring is going to be a big thing. So we can factor, I'm going to want to factor this, but I've got a sine and a cosine. So what I want to do is change it to be all the same trig function. Because I can't change this one, because it doesn't have the squared, I'm going to take this cosine squared and turn it into a sine squared. So leave this side alone for a minute. I'm going to replace this with 1 minus sine squared. Okay, so now I have the same trig function. We need to move everything to one side, so I'm going to add the sine squared over. So we have 2 sine squared minus sine of x, and then I'm going to subtract 1. So that's going to get rid of the 1 entirely. So we are going to factor here, but we're just factoring out a common factor rather than a trinomial. So I'll factor out a sine, which will leave me with 2 sine x minus 1. So either sine of x equals 0 or 2 sine x minus 1 equals 0. So that'll be sine x equals 1/2. So we're looking for the locations, again, between 0 and 2 pi, where sine x equals 0. So that's going to be at 0, pi, and 2 pi, but we don't include the 2 pi because of this bracket. And then sine of x equaling 1/2 is going to be, again, at pi over 6 and 5 pi over 6. Okay, so sine x minus cosine x equals 1. So I'm going to start this problem by adding the cosine over. But then we're kind of stuck. Now you could go through and just try to figure this out analytically, just kind of trial and error. What we can do though, because we know in the last example I was able to replace a sine squared or a cosine squared with a sine squared, but it had to be squared. So a strategy is to square both sides of this equation. The only issue with doing this is it may introduce solutions that aren't really solutions. So when we get our final answer, we're going to have to go back and check it in this original equation. So we'll go ahead and FOIL this. Okay, now I can replace this sine squared with a 1 minus cosine squared. Okay, and then we're going to move it all to one side. So I'm going to move it over to this side. So we're going to subtract the 1 from both sides and add the cosine squared. So the 1s are going to go away again. Okay, so I can factor out a 2 cosine in this case, which is going to leave me with a 1 plus cosine of x. So either 2 cosine of x equals 0, or 1 plus cosine of x equals 0. So cosine x equals 0, or cosine of x equals a negative 1. Well, cosine of x is going to equal 0 at the top of the circle and the bottom of the circle. Our x values are 0 there. Cosine is going to be negative 1 at pi. But I said we have to check our answers. When we squared it, we could have potentially introduced answers that aren't correct. So I'm going to take it and plug it into this original equation. Rewrite that down here. So I'm going to plug in these three values. So sine of pi over 2 minus cosine pi over 2. That's going to be 1 minus 0, which is 1. So that one works. If I plug in 3 pi over 2, sine of 3 pi over 2 minus cosine 3 pi over 2, sine is going to be a negative 1 minus 0, which is negative 1, which does not work. And our last one, pi that's going to be a 0 minus a negative 1, which is 1. So pi works, pi over 2 works, 3 pi over 2 does not work. Okay, this one here is going to be another factoring problem. We've got a trinomial. It's already equal to 0. So we know if I'm getting a 2 cosine, we're going to have a 2 cosine and a regular cosine, because if I multiply those, we get that. To get this negative 2, we've got a 1 and a 2, and one of them is positive and one of them is negative. So through some trial and error, if I multiply this 2 by a positive 2, I'll get 4, and then minus 1 to get that 3. So you guys can factor x equals plus 2 equals 0. So cosine x equals 1/2, or cosine of x equals negative 2. Cosine is going to be 1/2 at pi over 3 and 5 pi over 3. That's where the x values are 1/2. Cosine equals negative 2. Negative 2. Okay, can never happen. Cosine is not ever any less than negative 1. If you picture the graph or even on the unit circle, it's never below negative 1. So this one does not have a solution on that side. But these two are still valid answers. Last example here. Should be straightforward. We're going to factor out a cosine, which leaves me with tangent of x minus 1. So either cosine of x equals 0 or tangent x minus 1 equals 0. Okay, cosine is going to be 0 at pi over 2 and 3 pi over 2. Tangent of x is going to equal 1 at pi over 4, and then in the third quadrant at 5 pi over 4. Those are the two locations where the x and y are the same. The issue here is tangent. Tangent is undefined at certain locations. So these two are fine, but tangent is actually undefined at pi over 2 and 3 pi over 2. In fact, this setup, if cosine is equal to 0, that automatically means tangent's undefined there. So these two don't work because tangent is undefined. So those are some different strategies for solving trig equations.